Hello students, we are continuing with the last topic itself. In the last section, I was discussing about diffraction, how a bright fringe is formed, how a dark fringe is formed. In this section, we are going to derive the position for the bright fringe, position for the dark fringe, and width of the central maximum. Okay, so this section is the continuation of the previous section. So I already told the path difference. The path difference is written as d sin theta. Okay, path difference is d sin theta. And in the last section I told you, whenever the path difference is lambda, 2 lambda, 3 lambda, etc. n lambda, then minimum will be formed. That means dark fringe will be formed. Dark fringe is called a secondary minimum. So for nth secondary minimum, we can write d sin theta n is equal to n lambda. And since theta n is very small, sin theta approximately equal to theta. Therefore, what can we say? D theta n is equal to n lambda. From there, theta n is equal to n lambda by d. So theta n is equal to n lambda by d. That is the condition for dark fringe, or that is the condition for secondary minimum. Okay. Now, what is the condition for the secondary maximum? So we are going to establish the condition for the secondary maximum. We told if the slit is divided into 3 parts, 5 parts, 7 parts, etc. in all those cases we are getting secondary maximum. So for nth secondary maximum, I can just think like this: slit can be divided into 2n plus 1 equal parts. We are obtaining like this the path difference d sin theta is equal to 3 lambda by 2, or path difference d sin theta 2 is equal to 5 lambda by 2. Similarly, d sin theta n is equal to 2n plus 1 lambda by 2. So this is the condition for the bright fringe to obtain, or this is the condition for the secondary maxima. Secondary maxima means after the central bright fringe, all the bright fringes are called secondary maxima. Central bright fringe is special. Apart from that, all the bright fringes are called secondary maxima. So 3 lambda by 2, 5 lambda by 2, etc. 2n plus 1 lambda by 2. Again, when sin theta is very small, I can take sin theta approximately equal to theta. Therefore, what will be the change? D theta n is equal to 2n plus 1 lambda by 2. D theta n is equal to 2n plus 1 lambda by 2. So from there, theta n is equal to 2n plus 1 lambda by 2d. So this is the condition for the bright fringe, that means central maxima. So theta is equal to n lambda by d is the condition for dark fringe, that means secondary minima, and theta n is equal to 2n plus 1 lambda by 2d is the condition for secondary maxima, which is bright fringe. Okay, so these are the conditions for the minima and maxima. In both the cases, we can take n as 1, 2, 3, etc. Now, width of the central maximum. Width of the central maximum. Width of the central maximum means it is the distance from two minimas on either side of the central maxima. It is the distance from two minimas on either side of the central maxima. So from the figure, tan theta 1 is equal to y1 by d. You can see the distance is marked as y1. So the tan theta 1 from this triangle, tan theta 1 is equal to opposite side by adjacent side, y1 by d. Or since theta is very small, tan theta is approximately equal to theta. Therefore, we will write theta 1 is equal to y1 by d. Now, I already told central maximum is the spread on either side of the minima. That means, see, I'll just draw and show you. Suppose this is the central bright fringe. This is the next bright fringe. So this will be the fringe pattern. I want the width of the central maxima. That means this is the width of the central maxima. I write it as beta 0, width of the central maxima. From where to where I marked? From where to where I marked? I marked from the minima. See, this minima, first minima on one side to the first minima on the other side. That is why I told distance between the first minima on both sides of the central maxima. That is called fringe width. Okay. Now, d sin theta is equal to lambda, and theta 1 is equal to lambda by d for the minima. Okay, first minima on both sides of the central maxima. So we are taking first minima. So for first minima, d sin theta is equal to lambda. General equation was d sin theta is equal to n lambda. So here d sin theta is equal to lambda, and since theta is very small, sin theta approximately equal to theta. Therefore, we will get the answer as theta 1 is equal to lambda by d. So here theta 1 is equal to y1 by d. Here theta 1 is equal to lambda by d. So combine both, y1 by d equal to lambda by d. Okay, combining both the equation, you will get y1 by d equal to lambda by d. Then y1 is equal to d lambda by small d. D lambda by small d. That is the distance. Look at the figure carefully. That is the distance from the bright fringe towards one side. Similarly, I have to take distance from the bright fringe towards the other side of the minima. This is from bright to one side of the minima. Similarly, I have to take the distance from the bright fringe to the other side of the minima. That means 2 into lambda d by d. Okay, so y1 is capital D lambda by d. So central maximum is a spread on either side of O on the width. So 2 times of that. Therefore, beta 0 is equal to 2 lambda d by d. This is the expression for the central fringe, the width of the maximum. If they ask you, this width is called linear width of the central maximum. If they ask you, what is the angular width of the central maximum? So this one is called linear width. If they ask angular width of the central maximum, we got theta 1 is equal to lambda d by d, no? Angular width is actually 2 times theta 1, because theta 1 is this, only this part, 2 times theta 1 towards the other side of O also. So 2 times theta 1, because, so the answer is 2 lambda by small d. So linear width is 2 lambda capital D by small d, and angular width is 2 lambda by small d. Okay, in the exam you may think I can cut 2 and 2, then it will be theta 1 is equal to lambda by d. That is only half the portion. If they are asking angular width of the central maxima, you have to calculate 2 lambda by d. Okay, what is the difference between interference and diffraction? Interference is due to the superposition of 2 different waves coming from two coherent sources. Two different waves coming from two coherent sources, that is interference. But diffraction means there are no two coherent sources actually. Light is coming from a single slit. From the single slit, different secondary wavelets are coming, and diffraction is due to the superposition of those secondary wavelets coming from the same slit. That is the main difference. Now the second point, fringe width is constant for interference, and for diffraction fringe width is not constant, it is varying. And we studied central fringe. Central fringe is having twice the width, because just now we studied beta 0 is equal to 2 lambda d by d. The width of the other fringes will be lambda d by d. Central fringe width will be 2 lambda d by d. So central fringe is twice the width of the other fringes. Now all the maxima have the same intensity. We have drawn the graph also. Maxima is having same intensity, but here the maxima is of varying intensity. The intensity is different. There is a good contrast between maxima and minima. That means in interference, bright fringes are perfectly bright and dark fringes are perfectly dark. In diffraction, the dark fringes are not perfectly dark. Okay, and even the bright fringes, the intensity is varying. So there is poor contrast between the bright fringe and the dark fringe. So those are the differences. So with this, the diffraction topic is coming to an end, and they can ask you draw the intensity variation. So how will we draw the variation in the intensity? For interference, I already told you all the fringes are of same width and same intensity. But for diffraction, it is not like that. If I draw the intensity distribution curve, the central fringe will be having maximum width and maximum intensity. So this is the central fringe. Then width will decrease. This is how you have to draw the pattern. Here I am marking it as intensity, and here angle theta. So this is the central point O, and here theta is equal to lambda by d at this point. At this point it is 2 lambda by d, and here 3 lambda by d. Similarly, on the other side it is minus lambda by d, minus 2 lambda by d, and minus 3 lambda by d. So this is the intensity curve distribution pattern for diffraction. But for interference, we have already seen the intensity is same and the fringe width is also same. Okay, so that's all about diffraction. Thank you.